We know that tau equals I alpha. And alpha is the derivative of the angular velocity. Acceleration is the derivative of the velocity. So this is I d omega dt. If I is a constant, let's assume for the moment it's a constant, we could pull that into the derivative and we could write this as d by dt of I omega. But what is I omega? That's what we just defined as the angular velocity. Angular momentum. So what do we have? We have tau equals dl dt. The torque is the time derivative of the angular momentum. And this looks very much like the force is the time derivative of the linear momentum. Well, that's very, very useful. We said, though, that we could do this if the moment of inertia were constant. Well, the fact of the matter is that even if it's not constant, this is really the form that is true. It really is that tau is dl dt, and if the moment of inertia is constant, then we can pull it out, not the other way around. Actually, we started out with kind of a very simple definition for the torque in terms of the moment of inertia and the angular acceleration, but it's really the other way around. This is really the accurate definition for torque, and we can only come up here when the moment of inertia is constant. So what is this telling us? How can we use this? Well, we can use this in a very similar way that we used that the force was equal to dp dt. When there were no external forces, what did that tell us about the momentum? The momentum was conserved. Well, we end up with something very similar with the torque. With tau equals dl dt, when the torque from all external forces is zero. So, again, we're going to assume no external forces acting on our system. When that is true, then this is zero and dl dt is zero. And what does that mean? L is a constant, which is I times omega. So I times omega is a constant. The angular momentum does not change. It is conserved. Angular momentum is conserved. This actually has some very, very interesting results, and one that you might have seen if you've ever watched a figure skater. When a figure skater starts spinning around, and they start spinning with their arms out, and they start rotating relatively slowly, they don't have a whiteboard to move their arms around. What happens when they pull their arms and legs in? Well, when they move their arms and legs in, they're decreasing their moment of inertia. But if there is no external torque, and if their skates are on ice, so that it's very slippery and very little friction, then the angular momentum is just about constant. But what happens if I decreases? If they decrease their moment of inertia, what must happen to their angular velocity in order to maintain a constant product? In other words, a constant angular momentum, it has to go up. So what happens, and this is probably what you've seen, what happens when they pull their arms in? They start spinning faster. As I goes down, omega has to go up to maintain a constant angular momentum. Very, very good. Okay, let's take a look at a combination of translational and rotational motion. And we're going to look at a very, very specific kind of combination called rolling without slipping. I want to look at a motion that's a combination of rotational motion and translational motion, like this. Now, you can imagine, I'm going to have this tire on the table. Now, you can imagine that I could have a rotational motion that is much faster, so to speak, than the translational motion, and the tire kind of spins and skids on the tabletop. I might also have a rotational motion that is slow compared to the translational motion and looks something like this. Now, you might have experienced both of these with, if you've ever driven a car. Or you might have seen a racing car or something like that. If they're stationary and all of a sudden they give the engine gas and the tires start spinning, but the car hasn't had a chance to speed up yet. Its tires spin on the ground before it speeds up. Or imagine you're driving along and you slam on the brakes. Then the car keeps moving and skidding faster translationally than the tires are rotating. What I want to do is look at an intermediate case like that, where the rotation is just at the right speed so that the tire maintains contact with the surface all the time. It's not spinning this way too fast, and it's not skidding along this way with the rotation too slow. It's rotating at just the right rate so that it's constantly maintaining contact with the surface. Okay? That's what we call rolling without skidding. So let's imagine we've got this tire, this wheel of radius capital R, and at some point, let's say that a point on the wheel is in contact with the ground, say this point A, and then it rolls along, and as it rotates, A goes up, it rolls up, and it continues to roll along until A comes back down and comes in contact with the ground again. As long as the wheel maintains contact with the road, or whatever the surface is, as we said, now I called it rolling without skidding. I'm not sure why I said that. It's rolling without slipping. So let's imagine we've got this situation. So what can we say about it? Well, what's the distance that the wheel must rotate from this point to that point as it makes one complete rotation? Well, if the road is constantly maintaining contact with the wheel, that this distance from here to here must be equal to the circumference of the circle if the wheel is constantly maintaining contact and not slipping on the surface. So this distance, delta L, is the circumference of the circle, 2 pi r. How long does it take? How much, and by that I mean how much time does it take for the wheel to go from here to here? Well, to do that, it undergoes one complete rotation. So A starts at the bottom, comes to the top, ends up back down at the bottom. So how much time does it take for the wheel to make one rotation? Well, we know that omega is delta theta over delta t. And for one complete rotation, delta theta is 2 pi radians. So this will be 2 pi radians, and the time would be the period, t. So we know that the period is 2 pi over omega. What is the velocity of the center of mass of the wheel? So I don't mean the velocity of a point on the wheel like we were talking about before, the tangential velocity. I mean, what is the velocity of the center of mass of the wheel? How rapidly is the wheel? In other words, if this wheel were a tire on a car, how fast is the car actually moving? Well, that's going to be the distance traveled over the time. The distance traveled from here to here is 2 pi r. And the time is 2 pi over omega. So divided by 2 pi over omega. Multiplied by omega, we get 2 pi r omega over 2 pi. The 2 pi cancels, and we get VCM, the velocity of the center of mass, in other words, the velocity of the rotational axis as it moves along, in other words, the velocity of the car, is r omega. But you'll notice that was exactly the result that we got for the tangential velocity for a point on the rim going around in a circle. So that's actually the same as the tangential velocity we were talking about before. Well, what's going on? How did that happen? Well, let me redraw these diagrams and let's take a look. Let's look at these three situations separately. First, let's look at a wheel that is just translating like this with no rotational motion. What velocities do we have? Well, if it is moving at a velocity, a constant velocity, then a point at the top of the wheel will move at velocity v. The center of mass, or the axis of rotation, will move at velocity v. A point at the bottom of the wheel will move at a velocity v. So they're all going to move at the same speed. What if we had a wheel that is rotating but not translating. Well, then a point at the top of the wheel, we have moving to the right, your right, at velocity v. Point at the bottom of the wheel, we have moving to your left at velocity v. But the center, the axis, is not moving at all, so it's stationary. So we have a point at the top moving to the right at velocity v. A point at the bottom moving to the left at velocity v. And the center not moving at all. Now let's imagine that this velocity, the tangential velocity, is the same as the translational velocity for the center of mass. In other words, let's imagine that the velocity of the center of mass is equal to the tangential velocity, which we have already seen is omega capital R if R is the radius of our circle. And so, in that case, let's put these together. So this V, let's assume, is the same as that V. If we add these two motions together, what happens? Well, we'll have at the top, V plus V is 2V. The motion of the center of mass, we have V plus 0 is V. And for a point at the bottom, we have V plus negative V gives us 0. So what we end up with is the motion of points on the wheel look like this. The point at the bottom is always stationary relative to the surface. And that's the condition that we have rolling without slipping. There is no motion between the bottom of the wheel and the surface on which it is rolling. So that's just what we might have guessed. But then the center of mass is moving to the right at the velocity of the center of mass. But a point at the top is then actually moving at twice that speed. So whatever the speed is of the center of mass, the point at the top is moving at twice that rate. Okay, very, very interesting. Let's take and just let me back up one more second. So again, this result, to have the velocity of the center of mass equal to the angular velocity times the radius of the wheel or the circle, that is the condition for rolling without slipping. In order for an object to roll without slipping, we have to have this relationship. Very good. Now, I want to go one more step from here. Let's differentiate both sides. And what do we get? Well, if we differentiate with respect to time, v sub c, vcm, the velocity of the center of mass, we get the acceleration of the center of mass. And I'm just going to erase this just so I'll have a little room to put it down here. We'll get the acceleration of the center of mass equals, assuming the radius of the wheel remains constant, we differentiate omega. What's d omega dt? That's the angular acceleration. So alpha. There we go. So when we have a wheel that is rolling without slipping, if it's speeding up or slowing down, we also have a relationship between the acceleration of the center of mass and the angular acceleration of the wheel as it's rotating. Is it spinning up and rotating faster if the car is speeding up? Is it slowing down if the car is slowing down? Great. Let's take a look at an example of this. Let's take a wheel and let it roll down an incline and let's see what happens.